All right, party people. So we're going to move into talking about a new type of scenario, one we haven't considered before, and that's for adiabatic changes. Okay? So let's get to the slide and we'll set up the idea. So in an adiabatic change, recall, no heat is exchanged, right? So dq equals 0. So when we want to talk about a process such as expansion, when we talked about isothermal expansion, for example, we recognize that heat must flow between system and surroundings to have no net temperature change. So it has to be done in a diathermic container. If we want to impose this adiabatic change, then there is no heat exchange, and therefore the temperature has to change in the due course of an expansion or compression. So we can kind of view that if we look at this graph of T versus V, and we're going to find that the adiabatic temperature changes are related to this equation right here. We're going to derive that equation from this idea that if we were changing our volume without a change in temperature, our internal energy has to remain constant. However, if we're changing our temperature with a change in volume, then our internal energy does change, and it changes related to its heat capacity. So as we move down this curve, we recognize delta U has to be changing in order to fuel this expansion process, because there is no exchange of heat with system or surroundings. So setting that up, changes in temperature done adiabatically, right? Let's just remind ourselves, adiabatically, assuming that we can read and spell. I can't do either. So noting there, the first law, we start with du equals dq plus dw, and we imposed that dq must be equal to 0. Therefore, the internal energy change is solely related to the work done. Okay. So we recall that du equals cv dt, and because that's equal to work, that means that dw has to be equal to cv dt. Well, we have another way of relating changes in work due to expansion or compression, and that's from dw equals negative p dv, right? So we can plug that relationship in and arrive at the following. We can say that cv dt equals negative p dv. And now you can see we've got this relationship solely based on the things that are changing, the temperature and the volume. So we're going to do what I like to call divide and conquer, or we're not quite ready for divide and conquer yet, because we're recognizing here that this pressure change will be done reversibly as it tends on the ideal gas law. So we can make one more substitution. We can replace pressure with negative nRT over V dV, and now we are ready to divide and conquer. So we're going to put like things with like things. So we've got a dt over here, so I want temperature to come over into that position. So that's going to become cv dt over t. And now here we're left with negative nr over v dv. Okay. And because we've got our like variables with our like variables, we've done the dividing part. We can now conquer. So that's going to be taking the integral from initial conditions to final conditions. So on the left-hand side, that's going to be t initial to t final. On the right-hand side, that's going to be v initial to v final. Okay. So noting that, we're going to get two logarithmic relationships, right? The integral dt over t, or really dx over x, gives us that natural log relationship. And here we will assume that CV is constant, so that's another assumption here, that CV is not going to change over our temperature range, even though we know a wide enough temperature range it will. So this side becomes the following: CV natural log of T final minus T initial, and then that equals negative NR natural log of V final over V initial. Okay. And so doing some algebra here and some logarithmic tricks, I'm going to get all the constants over to one side. So we'll say that's CV divided by NR, and that's still natural log of T final over T initial. And then now I'm going to absorb the negative sign into this natural log and do a little algebraic trick. So when I absorb that negative sign in here, it flips the numerator and the denominator like so. Okay. And what we can finally do is now use another logarithmic trick. When we have something multiplied by a log, we can raise it as a power. So we're going to call the collection of these constants here CV divided by NR equal to some constant C. And I'm just going to do that to make life a little bit easier. So now I can rewrite this to be natural log of T final over T initial raised to the C power equals natural log of VI over VF. And now that we have this in this terms, we can take E of both sides and end up with the following. So that's going to be T final over T initial raised to some C power equals VI over VF. And noting here some algebra that can be done, I'm going to move the C over to the other side, and I'm going to move the T over to the other side. And that's finally going to allow me to write TF equals TI multiplied by the ratio VI over VF, and that will be raised to the power 1 over C. And that was that equation that I showed you at the very beginning. So awesome stuff here. Okay. Well, what about if we have changes in pressure? Okay, so we just noted changes in temperature. So now if we want to consider adiabatic changes in pressure, we will arrive at the following relationship, where now we've got this new thing here that I'm going to introduce, the adiabatic index, which is the ratio of Cp over Cv, which, recall, for gases, that there is a notable difference in those ratios, right? So setting up the ideal gas law, so we can say the following. We're going to note Pi Vi over Pf Vf has to equal Ti over Tf. So we're taking advantage of some gas laws here. So we've eliminated N and R because we're assuming those are constant. And so this is going to allow us to think about temperature and volume changes with respect to this adiabatic change. So we already noted, though, that that ratio Ti over Tf equals, it's going to be the reverse. It's going to be Vf over Vi raised to the power 1 over C. So we can place that there. So now we can say that Pi Vi divided by Pf Vf equals Vf over Vi raised to the power 1 over C. And then now doing some algebra, we can rearrange this and come up with the following. Pi over Pf. And then what I'm going to do is multiply. I'm going to cross multiply to eliminate, or to really combine the VIs and the VFs. So when we do that, I get VI over VF. So I multiplied both sides by VI to the 1 over C power, and multiplied both sides by 1 over VF to the 1 over C power. And that gives us the following. The exponent becomes 1 plus 1 over C, and that all equals 1. Okay. So now we've got to figure out what to do with this constant here. So let's play some algebra with that constant. 1 plus 1 over C. We know that doing some algebra, we can call that 1 plus C divided by 1. So I just multiplied the top and the bottom by C. And then now, noting that we recall C was equal to CV over NR, or equivalently, that would be CVM divided by R, right, where we absorb the number of moles there into CV, right? So now we can plug that in and say 1 plus C is 1 plus CVM divided by R. Oh, I made a mistake in my algebra. So that was 1 plus 1 over C. That becomes 1 plus C divided by C. Apologies. Hopefully you caught that. Perhaps you did, perhaps you didn't. So multiplying both sides by C over C is how we get that. Okay, so then now that's divided by CVM over R. Okay. And if we continue playing with this algebra, this will become R plus CVM over CVM. And this is pretty cool because earlier we said that the difference between CV and CP is 1 unit of R. So this becomes CPM over CVM, which we noted is equal to our adiabatic index. And thus, this 1 plus 1 over C just becomes gamma. Okay? So now that gives me PI over PF times VI over VF raised to the gamma power, all equals 1. And now rearranging that algebraically, we get to that top expression, right? That becomes PF VF raised to the gamma power equals PI VI raised to the gamma power. So what is the big deal of all of this algebra that I made you all look through? Well, if we go back to our ideal gas surface equation here, right? And before, when we were looking at our individual gas laws, we were identifying our isotherms and our isocores and our isobars. So what I want to note here is in our isotherm, let's highlight that, right? That will describe isothermal expansion. So expanding or even compressing an ideal gas. Because it's an isotherm, let's highlight that, right? That means temperature must be constant. And for temperature to be constant, that means it has to be diathermic. So heat has to be able to flow in and out of the system to fuel that change. However, when we are dealing with what I'll now refer to as an adiabat, let's highlight that in blue. This describes now trying to do that expansion or compression, but this time without an input of heat from system to surroundings or vice versa, right? So you can see on this graph now, temperature of the system has to be changing in the due course of an adiabatic expansion. So, and you'll notice here that if we look at this on a 2D slice here, because our adiabat is proportional to 1 over V raised to the gamma power, it's falling off more steeply than is the isotherm. Okay? So now, of course, because our molecular modes store energy, and because there's nowhere else for us to get energy from in an adiabatic process, our monatomic gas, our linear gas, and our nonlinear gas will have different adiabats. So they will have different temperature changes because of the way they store energy in those modes. And as it turns out, we can find what these powers are by just looking at the simple relationship, recognizing that CPM equals CVM plus R. And if we recall what CVM is for our various gases, we can get to these relationships. Okay. So for example, CVM for a monatomic gas was 3/2 R. Okay. And CVM for a linear gas was 5/2 R, and CVM for a nonlinear gas was 3R. So if we go back and look at that gamma, once again, gamma being CPM over CVM, then we arrive at these following relationships, right? So gamma for the monoatomic gas. So I'm going to replace CVM with CVM plus R divided by CVM. And when we plug in that 3/2 R, right, we're going to get 3/2 R plus R over 3/2 R, okay? And doing some quick algebra here, that gives us 5/2 R divided by 3/2 R, meaning gamma is 5/3. And we can repeat this same process with our linear gas and our nonlinear gas and arrive at these adiabatic indices. And okay, so what this tells us when we think about the temperature changes that these different types of gas will experience upon adiabatic expansion, a monoatomic gas will experience the greatest temperature change due to the index right here. So that 5/3, that's got a value of 1.67. That 7 over 5 has a value of 1.4. And 4/3, that's a value of 1.33. So because the adiabat here is dependent upon 1 over volume to the gamma power, that monoatomic gas has the greatest value of gamma, so it's going to have the steepest slope. So that's what the math tells us, that there's going to be the steepest slope and thus the greatest temperature change for the monoatomic gas. The way we can interpret that with respect to our degrees of freedom is the nonlinear gas has more degrees of freedom to store energy. Therefore, it will experience less of a temperature change as it's able to use its own molecular modes of motion for that energy storage. Okay, folks, we'll explore this more in the live lecture. I'll see you then.